Okay, good evening. Buonasera. Buonanotte. My name is Keith, and you can find my LinkedIn profile over there, the QR code. And if you want to do some study about the product solution, this is the application notes QR code, so you can just have some fun with it. And I'm going to talk about the zero latency video. Zero is a relative term, okay? It's according to Einstein. Same as when you observe the North Star. Someone mentioned the North Star a few weeks ago. No, last week. So when two observers looking at the North Star, the difference between the two observers is zero. That is what we intend, not the 433 years of light year from us to the North Star. The distance is the 433 light years. So the zero latency is watching the North Star between the two observers is zero. So please try to not to take the photo or video on that TV. We are doing a demo because we do not have the content right. It's just a technical demonstration to show you that we are capable to do live streaming over public internet, over CGNAT, carrier grade NAT address translation, over the Wi-Fi in this building. And the round trip delay from here to the video source is around 108 milliseconds I last measured. Probably now it's getting higher because all you guys are in here using the Wi-Fi and the latency will be much higher. So live event, I guess you guys already noticed that live event is not easy thing to do. Someone did something really nasty last Friday, and I'm not going to mention that. Against the video on demand is completely two different things, okay? Why and how? Live event, you need to have a real-time content, immediate reaction, real-time viewer engagement reaction, so you're texting everyone and saying go or whatever. Latency must be minimum, and the concurrence is extremely high. Typically 50%, last 5 days were under 30%, 40%, something like that, to 70%, which we empirically measure that in one of our customers. Once we measured that was 100% concurrency. That was really scary. During the World Cup, Uruguay against Switzerland. During the halftime, someone changed the channel and watched the same channel all together. That was quite scary. Video on demand is the pre-recorded content, anytime, not real time. Okay, so you can just watch it whenever you want. So it's completely very relaxing for the server to serve the video because you can have a buffer or rebuffer, wait for 1 hour, 2 hours, no one cares. The concurrency is extremely low. And this 2 to 3% is, we measure that the information come from our customer. So most of the people who watch the same content, concurrency is only 2 or 3%. That is extremely low, okay? The highest one is in one of the SWOT vendor, so provider, is around 8%. The solution I'm going to present, we're using all this standard. Nothing special or need to be developed in next 5 years or 10 years, like the other guys. And we use all RFC already in place since 2000 something. And for the video contribution, we use 2022-7. Okay, so we can use one or multiple stream and sending the contribution to the edge. Okay, so it's also for contribution and distribution as well to the edge. And then the rest of it is just standard MPEG transport stream, wrapped in RTP over UDP. So a lot of people say that it's not possible. That is the demo over there in the back. So you can do it, you can try it out. We stream Ultra HD and HD from a very long distance to here. We can handle up to 40% random packet loss. If you cannot have a 40%, I can get my impairment 2 come out, and then we can have fun with it. Okay, it's 30%. We can also sustain up to 50% of periodic packet loss. For example, you lost 300 milliseconds, 100% open circuit, and then 300 milliseconds, no loss. So we can have a perfect video without any problem. The formula to do that is very simple. If you have done the engineering in university, year 1, they teach you that. Okay, it's a simple control algorithm. Okay, you just write the formula of the model of the system. You do your set transform, S operator, and then you do the set Z operator. That's it, second degree. So, zooming in, what we are trying to do is tackle the latency and the drift. Okay, drift is being measured quite a lot by a company called Phoenix Real-Time Solution. Each year, during the NFL Super Bowl, they typically measure the drift is between 30 seconds to up to 90 seconds. Okay, it's well documented. And we are trying to zoom in the problem of the net zero, because everyone using a lot of server in the data center. At the moment, the data center is a hell of a lot of problem because we need to a power plant next to the data center to power it up. And the drift, I already mentioned that. Okay. One thing, OTT delivery is operating the best effort only. Okay. So wherever you do the OTT, it's best effort, and that is extremely difficult to do in the open internet, in real-time transport and real-time transmission. You can use a TCP, but head-of-line blocking, every packet loss, you need to wait for the packet retransmit before you come back. And then you can look at the Matrix equation, and then you will tell you that the error will go up, and then you will lose your TCP, and then you will continue rebuffering. Okay. End-to-end architecture overview, simple, resilient, and infinity scalability. Infinity scalability because we're using multicast. Okay, we can do multicast and unicast. It dynamically adapted to the network and device capability. If the device and the network can support multicast, it will switch to multicast. If the network does not, the segment cannot support multicast, for example, fixed wireless SS network, using one of our competitors' radio, and they do not support release 17 multicast PIM, and then we can also support that by continuing using unicast. The same protocol, everything same, and the change is that the surface router, which is the delivery mechanism, change the multicast group to the destination IP address and port. Same payload, everything is the same, just change the packet destination IP address. So it's a packet replication and packet forwarding. Simple. We can do 8 million concurrent sessions in one single strike. Okay, so we can have up to 8 million. And the capacity of the egress of the surface router is, the smallest one is 1 terabit, the biggest ones are 216 terabit. So someone had a 700 terabit, so we can just use 4, and then we can cover the whole entire globe capacity. Okay, so if you put a few more, and then you can scale up a few hundred petabytes. So the solution is very simple. It has the video head end. We have using the conditional access or DRM. It depends on what you need to do at the edge, in the end. So we can pre-condition and scrambling it, or someone do the scrambling, and then we just optimize the MPEG transport stream for IP delivery. And it's 1+1 pair. You can have a geo redundancy. We have the synchronization all over the globe. So it's MPEG transport stream. It has the timestamp. And also we are using RTP. It has the timestamp as well. So every single packet, they are all synchronized. It can go through the public network, core network. So in case of the core network having some problem, it's called core network convergence. It can have 8 seconds of a breakage of the stream. Okay, a lot of people are not aware of that. So if you have a core network convergence, you will lose 8 seconds at least. So what we do is we are using the ST2022-7 using multiple paths. I think this guy been using that in the past, LTP. Yeah, it's LTP 2022-7.
No, it's worse than that.
But they changed to something else. So we just deliver as far as we can. For example, we can put another service router in New Zealand. So one in here, then, or make it easier in Latin America. So we can just put the perfect stream, two or multiple synchronized stream to the edge. And then the edge will stitch them all back together as a one single perfect stream. And then we can support a mobile network, fixed wireless access network. People always say that 5G is very good, very high bit rate, but the problem is that 5G is the side of, you have to be direct side of light, so you must see each other, otherwise there's a wire in the middle, and then you put a break all in the middle, so the attenuation of the signal will go down. From minus 30 dB, you can go down to minus 60 or minus 90, so you will lose all your bandwidth and your capability. And we also support that as well. And we have N device is a library sitting in the mobile phone or set-top box or smart TV. We already done the integration with Tyson. Tyson is a Samsung Smart TV OS. So it's been in there or sitting in your TV at home already since 2019. Okay, if you bought a TV after 2019, you probably have our software already in there, but Samsung will not enable it until you pay them. And also, it only works with Niagara for some reason, okay? I'm not going to say it, therefore. And we can support the fiber or twisted pair, so it doesn't matter. It's any access network, the same protocol and same packet transferred all the way to the edge. We can also support CMTS. It's a cable solution. So the cable, when you join the multicast, we've been measuring that the delay of IGMP join is 7 to 15 seconds or bigger value. So what we do is that during the channel swapping, we send the unicast to the device fast enough, and then bufferize that what you can do. I hope you guys all know what's the MPEG transport stream. It has the encoder buffer. It's called PTS minus PCR value or decoder buffer. So we just make sure that the device can fill up those buffer quickly as possible. So while you fill it up, we also continue decoding and presenting on the stream. So that's why the channel change time is extremely low. If you have a one chip delay, it's around 1 millisecond or 10 milliseconds, and your iframe is 80 or 100 and something milliseconds, so you can change the channel within 19 milliseconds or even lower, depends on the size of the iframe. If anyone tells you that, lower than that, you need to ask the question, what's the size of the iframe, okay? Mathematics is not opinion, and you cannot travel faster than the speed of light unless you're on the edge of the universe, okay? And so we can do also OTT onto a third-party access network or third-party router. So it's very simple, okay? It's whatever you have in your network, we can do that. All you need to do is just put the extra card on the service router. That's all the hard work. So from the cloud to the pocket, we're going to use the Cortega. Cortega is the OCI. It's Open Container Initiative back in 2015, something like that. So we virtualize your CDN, the origin, the DA, packager, everything into your app, because you only need to serve one stream, okay, in your mobile phone to be backward compatible with HAS, HTTP adaptive streaming. So I'm going to explain in a minute. So the objective of this is to reduce energy consumption, reduce the CapEx and OpEx, because you do not need to pay Amazon AWS anymore. All you need to do is just build your app, sell to the customer, that's all. And the electricity bill will be paid by the customer, whoever watched the TV or watch it on the mobile phone. So that is the objective. And this great idea was done by two guys sitting in this room at the moment, Jorge and Juan. So over there. They are the father of this idea. They did the POC back in 2019 with one of the customers in Spain, yeah? So what do? We have a problem. CDN in the pocket, we use the Cortega. Cortega is the OCI container, Docker. You just put everything in your Docker and then put into your app. So it will reduce the offset zero latency live streaming, enable the extended contribution feed, enhance the streaming quality and responsiveness. Okay, so you just stop it, you will do the fast channel change, and you receive the MPEG transport stream. Okay, from there you just segment it, because we already pre-conditioned the stream to be perform the segmenting. So you do the CMAF, and that piece of idea was done by Jorge and Juan. So if you have AWS, don't blame me, because someone already come up with the idea a long time ago, and they even patented it. So we can, after CMAF, you can do the HTTP server on your device, which down to your OS. Or you can want to have a very, very fancy one, it's the MOQ, but it's not yet ready. So you can also do that, because CMAF can just be simply, you can send it to your device. Funny thing is that the device is zero distance from your HTTP server. So the probability of packet loss is 0. And the distance is 0. The time required to transmit is 0, 1 millisecond, or let's say that. So subsequently, we remove all the TCP deficiency and use the maximum capability of TCP. Just send it to the player. It's backward compatible with all the browser, all your existing app. Okay, all you need to do is just build this app. Put it into your mobile phone, home gateway, or vMac. Okay, because in your home gateway, the distance still a little bit. You can lose some packet, but the probability of loss of packet is still very low. Okay, but you also, the distance between your TV and the home gateway is probably 1 or 2 millisecond round trip delay. So you can, or your headset, you can do the retransmission quickly. Okay, before they even noticed. So this is how it works, and it put into your pocket. Currently, we are looking for partners to build this app, because we are not the one who built the origin or CMAF segmenter or whatever. So if you guys are doing the CDN, you have the opportunity to build this app and be the first one in the market, and then you can compete very well. Put yourself in the advantage position. So we can backward compatible with HLS, Dash, whatever. We support DRM, because the encryption from the video end, we don't touch anything. We just pass through, and then we optimize the MPEG transport stream, and that's it. So you can already encrypt that, and then someone will fetch the key, or pre-fetching the key when you tune to the channel. Okay, zero latency streaming against traditional broadcast and OTT streaming. The starting time is been measured by our customer during all the acceptance testing. And we are more or less here, because we send the iframe and the audio packet, and the time required to receive the iframe and audio packet, we start to decoding, because we are sure that the server the router will continue sending the packet to the edge, so we can start the decoding straight away. You do not need to wait for the PTS minus PCR value. That can be 300 milliseconds up to 1.8 seconds. Okay, so we can start to decode because we alignment the audio and the iframe together. That's another patent by NOKIA Bell Lab guy. The guy is not in here. I tried to ask him to come along, but he says he's too busy with all the kids. He has 6 kids or no? Yeah. Oh, wow, 6, huh? 4 or 6? 4. Okay, 4 kids. So he's so busy, and so he cannot come, and he has 40 patents, more than 40 patents. We are using approximately 12 or 15 patents of him in our solution. So we compare with digital terrestrial TV and satellite. We are much faster. With IPTV, with multicast, with fact, more or less the same because they need to wait for PTS minus PCR. It's not opinion, okay? It's the impact transport stream. That is what. With the ultra low latency stash, you can little bit can be higher. Someone measured that using the Amazon Prime Video. That is the benchmark of Prime Video. Okay, and the last one is the BBC iPlayer. Okay, someone did that measurement, and then it's quite high, 14 seconds starting time. And live latency, since we do not caching, we do not do segmenting, we do not do anything to the impact transport stream other than just packaging it using RTP and send it out as far as we can. When we receive the impact transport stream from the video head, we just push out. So then, and also this way, you build up the buffer in the device, so we do not have extra latency compared with the digital terrestrial TV because we are all using the impact transport stream. The same what I described in the earlier is 2 observers watching the loft star. We have 0 latency between the 2, but the loft star is a 433 light year from here. Okay, and from the cable as well, and the traditional IPTV and ultra low latency. Because those guys are using TCP with the random packet loss 1 to 30%. They will be to infinity because we measure the TCP round trip with round trip delays 30 milliseconds. The latency will grow to infinity. I did some testing with the AWS Prime Video using Carafun. It was terrible. It was in the beginning of football match. It's around 9 seconds to 12 seconds with 3% random packet loss. It grew to around 21 seconds in 1 minute. And then after half time, it's around 200 something seconds. Okay. And I also tested one from a company in Northern Europe, and they had the latency very, very low. HLS, ultra low latency, is around 300 to 500 milliseconds, extremely low. After 1 or 2 minutes, the drift become around 5 to 6 seconds and 10 seconds. After 15 minutes, it completely stopped because the buffer underrun on the server side because it ran out of buffer because it kept asking for retransmission. So we've been doing all the empirical testing, and I travel always with my impairment tool. It's in my bag. If you guys want to try out, I can impair the packet as you wish. We can impair 1 to 100% random packet loss, and then you can have fun to see what happens. Also, another thing is that I verify what happened. Is OTT or IPTV to this is the set-top box from from Telefonica, 18 years old, and we can still receive video quite nicely from Denmark, from Spain, and from my local multicast. This is V Sport, is the YPay, and we have the mobile app from iVidia, RTRK, our friends in Serbia, and we just give them a library to receive the MPEG transport stream over RTP, and they did it in 1 hour. Okay, that is the sort of time required to integrate our library into the existing app, which has been deployed in France and India. Multi-millions of app they've been deployed and like that. It's just standard MPEG TS receiver. So you can see that it's from Spain TV and from Denmark. So the same app and same transport stream, if it's anywhere, we just tune to different server, different IP address. Okay, case study. Okay. Some of the content may have the copyright, and I just use them for comparison of the technology, where we are, and how good we are or how bad we are. Okay. This is case study of a sport event live, and we compare with global CDN, with Big A, you know who. And then our solution and also OTT, both of us, our OTT, we are approximately 67 seconds ahead, more than 1 minute after 2 hours, 1 hour something, okay, 1 hour and 40 minutes, and they're drifting all the way. It's ultra low latency. It's low latency and drifting up to 67 seconds. Compared with the broadcast TV, we are approximately 2 seconds ahead. Okay, so reason very simple, because when you sending the signal from your production to the antenna, you have the round trip delay. You have the signaling using whatever CC or RTS or RTP. You have time from the antenna. You need to convert it into a radio signal, and then radio signal, and then have latency, and then arrive at your TV, and so you have a approximately 1.3 seconds, but we measure 2 seconds because we cannot see the digital point after the 2 second resolution. We compare with the betting website, and this is the betting website, and this is our solution. This is Canadian women football, and we approximate the same time. Sometimes they're faster, sometimes we are faster, depends how quick they flash the web page. Okay, they just need to push out, and the web page is, I've been talking with one of the guys in Sport Pro, and they provide this offer service to the website, and they told me there's around 40 millisecond delays from the time they push it out. Okay, but pushing out is using TCP. TCP have head of line blocking, so sometimes they're later, sometimes they're faster. So it's average, we are the same. This one is more fun. It's 2015, so around 9 years ago. We already have a multi-screen, multi-view, Formula 1, Singapore. And we just, you can select your car and your view, and then have the audio. Actually, they have the multiple audio as well, so you can have the commentator or some fans to make the audio over the video, and you can pick whatever you need. And this system, I saw that also in the Olympic channel today. I visit the Madrid office, and I realized that they have the same equipment inside. And when I saw that, I said, wow, okay, we are using the same thing. This is for reference purpose only. This is Rai Uno at my home. I live in Italy as well as in UK, because my wife is Italian. Okay, and I've done the military service in Italy as well. Okay, so we are watching I was watching the TV in Italy, and I realized something wrong, because I watched the other channel from my customer. I was testing it, I was impairing it, and try to reach 40% random packet loss. And it does very well, no problem. And then I realized that it was 2 seconds ahead of digital broadcast TV in Italy. And this is streaming from UK to Northern Europe, and then back to Italy. The round trip is around 2,000 kilometers. So you can calculate the round trip delay. So we are approximately 2 seconds, so we can do that. It's just for reference, so show you that this is not a nonsense. Okay, this is real. If you don't believe it, the demo is over there. This is more fun. I was watching the basketball, NBA, over the satellite signal. 8 minutes and 13 seconds is countdown. Basketball is countdown, okay? 8 minutes. So we are 13 seconds ahead of the satellite signal because they need to bounce up the satellite and then come down to descramble it, and then we encode it, we scramble it, and then send up the satellite and come back down, okay? Someone's from Israel did all those descrambling and encryption and then send it up to the satellite coming down. I think you guys know who they are. And that is around 13 seconds. This was more fun. And this, I was streaming from Spain. I was in Rome during the exhibition conference. And the football match started at 21:00. So now the time I took the picture is 2 minutes and 45 seconds. So we are approximately 15 to 17 seconds behind the stadium. Okay, that is quite good. And that is the TV local. And then they have the same feed from the provider, UEFA. And we are identical latency. Okay, zero latency. It's 2 observers. Of course, that's a 15 seconds behind from the view from the stadium event. And this one's more fun. I was getting bored on the way back from Hong Kong to UK, and I was on the airplane, so I paid $18 for the Wi-Fi. And I said, okay, I'm going to watch TV on my mobile phone. So I start to watch them. I cannot record a football match because I was watching football match. Okay, so I picked our customer's advertisement channel. So they are perfectly video, 1.2 second round trip delay. The packet loss is approximately 20 to 30%. It's perfect, no problem. UDP. Okay, if anyone tell you that UDP cannot be used due to the packet loss, you should tell them to go back to university, study first year engineering. It's called control theorem, and you just do the Laplace transform, and then you do the S operator and do the Z operator, and then that's it, you get the formula. The number of line of code is 6, okay? You can make it happen in 6 lines of code. You take your approximately 1 hour because embedded software is around 6 lines of code per hour. So this what look like, and then you can see that the airplane mode on, and Wi-Fi is on the airplane. So the key takeaway: simple, resilient, flexible, scalable, and sustainable. Sustainable because we do not have the caching, we do not have the origin, we do not have a cloud. Okay, no more cloud, sunny day only. Okay, no more rain. Okay, so we use a RTP, which is the real-time transport protocol over UDP. It's capable to comparable with the OAT, over the air, DTH, and no caching and no buffering. That is the key. No delay of whatever in your streaming. And it's a zero drift because if we lost the packet and we cannot retransmit it, we use the decoder to mask the error. Okay, you can do that. Most of the modern decoder can mask the error of the vector error, motion vector. So you can do that. Actually, there's some error in there, but the Broadcom chipset does all the magic, mask the error. Okay. And some sort of jitter, but you cannot see it because we have done some trick on that. Actually, those code over there is RDK, is open source from RDK Wiki, is Apache 2.0, so you can use that code if you can get your hand on it. It can tolerate up to 40% random packet loss. If you do not believe it, I can do the impairment and show it in front of your eyes. And then you can use the Wireshark capture as well, okay? And 50% packet loss, for example, 300 millisecond of packet loss, and 600 millisecond no loss in total. So it's a 300 millisecond no packet loss. So how the hell are we going to retransmit 300 millisecond in 300 millisecond? It's very simple. Go and study in university. First year, they will teach you that. It's a time division, okay? So how we can accommodate from 1 millisecond to 3,500 millisecond. The reason why I'm choosing 3,500 millisecond because I need to go to the moon and back. It's more or less a 3,000 millisecond. So we are moon landing ready, okay? It's just waiting for someone to go up there. We can deliver the last packet as far as we can, so you can do the channel serving. So you can go there and test it yourself. And then also we optimize the stream adaptive, both multicast and unicast. As I mentioned that, if the network on the device can support multicast, it automatically fall back to multicast. If the network or the device cannot support multicast, it uses unicast. It's a router unicast. Okay, it's just the router does the trick. Replace the multicast group with the destination IP address in the port of the device which requests. That is the device open the CGNet port, okay, session, and you just send it to that. Nothing tricky. It's standard routing protocol. It's been around since 1995 by the company in San Francisco with a funky link. And also we can cable to support temporary localized congestion. For example, if you want to have fun with it, you can launch the speed test. It's the worst congestion creator you can have. So you can launch 1 or 2 or 3 speed tests in different devices and then go to the same subnet, and then you will cause the packet congestion. And then the router or switch will start to drop the packet. We can sustain that. Okay. That's all. No Q&A, I think.
No Q&A works.
Okay.
Thank you very much.